So some administrative issue first. I got approached by a few students telling me that they are caught up with their work, so they are not able to hand in the homework on time. I know that most of you are working adults, but just approach me 1 day before or 2 days before. I don't think it's fair to other students, because some students probably rush to finish the homework. But I also don't want to say that, okay, you get penalized because you cannot hand in. So the compromise is this. I will extend the homework submission till 2 days later, which is 13 April. But if you hand in on time, by 11:59 today, no penalty. Okay, no penalty. If you hand in tomorrow, consider late submission, I will impose some penalty. If you hand in 2 days later, more penalty will be imposed. Fair? Okay? So if you got caught up by the work, you cannot finish today, fine. You can still have 2 days to submit your homework 3. Those who have finished, do submit on time. Okay? If you approach me earlier, I probably would apply the same delay or deadline, extended deadline to everyone. But you only approached me yesterday. I think it's very difficult. I know that some students probably work on it very early, so it's not fair to them. Okay? So I have to impose penalty. Now, second thing, some of you asking about the final exam. Final exam, you are free to bring anything. Anything. So you can bring iPad. Try not to bring laptop, because very difficult for us to know whether you are communicating or searching. You get my point? Okay? So if you are searching through the lecture note, you don't want to print out, you want to search through the lecture note, you have some tablet, that's fine. You just scroll, right? I don't want to see you guys typing. Okay? But if you are using laptop, when you are doing some typing, you will raise some concern. I don't know whether you are chit-chatting with somebody to get the answer or what. So you can bring printed copy as well. Okay, we don't care. It's open book. Usually that doesn't mean easy exam. Okay, open book. Some students think, oh, open book, good. I don't have to memorize anything. Yeah. But it also means anything can come out. Okay? For the project, I don't know whether you guys have attempted the project. Haven't? The deadline will be next Monday. I cannot extend it further. Okay? Because next week will be reading week already. You need to give me some time to grade. Okay? You already see the way I grade homework 1 and homework 2. Homework 1, even you don't get back the graded homework because it's Excel. I do give comment. Okay? What are the things that you do wrong? And then for homework 2, I do grade it and give the comment as well. Okay? I intend to do it the same way for homework 3 and also project. So I believe this is better in terms of learning. You know what I'm looking for, what are the things that you fall short of. Okay? So you need to give me some time to mark. You cannot be like, you hand it 1 day before the deadline, then I don't have time to grade and also consider carefully how to give the mark. So 18, probably no extension. Okay? So try to stick to the deadline. Today is my last lecture. I hope you have fun so far. Okay? A lot of students encounter the issue of quota. Running out of quota in your server or whatever the workstation that you are doing. Now, university are very stingy. They only give you probably 200 meg or 400 meg. I can't remember the quota. So when you run the simulation, don't run on your home folder. Extend it. Set out your simulation folder under the /var/10. I think I mentioned it during the workshop. Okay? These actually have enormous amount of storage. You can use it. The only bad thing is that after 2 weeks, it will gone. Or it will go. So if you want to save your simulation result, you can transfer it to your own home computer. Okay? Simulation usually take up quite a lot of spaces. Especially you run transient and you run long time. Okay? 5 steps. It will take out a lot of spaces. So if you run into the quota, there are a few commands that you can use. du. So you go to the folder, du, you will list down the size of each file, and then you will know which one take out a lot. And then you can decide whether they are important or not. If it's important, you back out. If it's not important, just delete it away. Simulation file, usually I don't consider it as important because you can rerun the simulation as many times as you want. Okay? You're not dealing with very complicated system. For design in the industry, usually they take days to run. So they cannot just anyhow delete the simulation. But I believe in your case, probably within minutes, the thing is done. So if you really need to relook at the result, you just have to delete and then rerun. That's all. Okay? Now, last week, we talked about frequency compensation. Okay? We talked about a few techniques. For example, lag compensation. The simplest one is just change the load capacitance. That is lag compensation. The good thing is very simple. The bad thing is you only change one pole, the dominant pole. So using this technique, you can get the phase compensation, but the bad thing is it's going to lead to low frequency design. Okay, and the capacitor is going to be tremendous. And then we also talk about another kind of lag compensation using Mueller cap. The good thing about Mueller cap is that it makes use of the amplifier gain to boost up the capacitance or to boost up the dominant pole. So one advantage right away is that you don't need to burn a lot of capacitance. Okay, you can achieve the same phase compensation with smaller capacitor. Second thing, because now you don't just simply move the dominant pole, you also move the non-dominant pole. So this is what we call pole splitting. And because of that, you can actually end up having higher frequency than just simply adjusting the load capacitance. And then we also talk about the lead lag compensation. So the key concept is that what if I remove the zero? Okay, I remove the zero. I insert the register in such a way that I can remove the right half plane 0. So in that case, I successfully eliminate another component for phase lag. And the good thing is that you will achieve much higher frequency compared to the lag compensation technique. And finally, the lead compensation go one step further. What if I not only want to remove 0, I want to move the 0 from right half plane to the left half plane in such a way that I can actually cancel out the non-dominant pole. So in that manner, I actually fundamentally achieve the so-called one-pole system, and the system will be always stable because one-pole system only got 90-degree phase shift. And in that way, I can actually get as wide band as possible. And of course, we go through all these things. The reason people want wide band is mainly because they want faster settling. So you hopefully know by now that settling behavior is related to the bandwidth in a manner of 6.9 divided by the bandwidth in radian per second. Okay, RC time constant. And we also introduced to you what is the concept of doublet, what caused the doublet, and finally, very importantly, the slew rate. So slew rate actually causes non-linear settling behavior, although the settling behavior looks very linear. Okay, I explained that also. Now today, we are going to look at some OM design, but trying to target at different things. So we look at different kind of OM that will actually get your gain further boosted. Okay, for example, the telescopic, the folded cascode, the gain booster OM, and we also look at the differential OM design. In fact, the so-called differential to single-ended output, the typical OM design or the typical OM that you will be encountering in the market is usually single-ended output, differential input. But in IC design, a lot of time we don't do that. We actually prefer to use differential input, differential output design. Okay, the reason it provides better common mode rejection, which means if you have noise, if you have interference, you are better in new. Okay? Of course, the drawback is more complexity. More complexity. We'll look at that. And we also look at how to boost the performance further. Here we don't just talk about the gain. We talk about other things. For example, we want the offset voltage to be smaller. We want the noise to be smaller. Okay, what can be done? Okay. Finally, we'll also talk about some common mode feedback circuit, which is needed for differential op-amp. So let's take a look first. Now you have some idea about the op-amp design. So one thing that usually students puzzle about is that, yeah, I know how to design op-amp. Yeah, I know what kind of gain I'm getting. But so what? I know my op-amp achieve a gain of 60 dB. I know my op-amp has GBW of 10 megahertz. But what is the implication? I usually use the op-amp to design some ADC. How do I know that the op-amp parameter is sufficient? I use it to design some filter. How do I know that this kind of op-amp parameter is okay for my filter design? Remember, op-amp is always a building block. So whether this building block is sufficient to be used in a system or subsystem, you need to answer that. And that is usually puzzle student. They know I need op-amp, but they don't know what kind of op-amp is sufficient. Okay? So let's take a look at the design. A very commonly used design, sample and hold. So you use op-amp as a sample and hold circuit block. So sample and hold is key building block for ADC. You try to sample the incoming signal, hold it, so that the subsequent ADC can process it accordingly. So here, I just use a very simple unity gain buffer sampling hold amplifier. Okay? So you can see that when you sample C1, okay, and then you will hold it under C2. So now, whatever the V out, I can do subsequent processing. Okay, I can do subsequent processing. So here, further illustration. So during phi 1, your phi 1 switch closed. So whatever the charge as your input is being charged up to your C1. So you can see that your C1 is being charged up. And at the same time, your C2 is reset to 0. You want to throw away, forget about what had been installed previously. So your C2 is 0. Okay? So your V out, you can see this guy closed, so V out equals to 0. Here, we ignore all the non-linearity of the op-amp, such as offset voltage, all these things. Now then, during phi 2, you already sampled the C1. Then during phi 2, your phi 1 switch open. Your phi 2 switch closed. Now when your phi 2 switch closed, this is closed, this is closed. You can see that you're trying to force the voltage across C1 to be 0. That is obvious because the left-hand side of the C1 directly connected to ground. The right-hand side for C1 is connected to the so-called virtual ground. Because of the op-amp, it's forced the inverting input to be ground. So you can see that the C1 is trying to go to 0. But you know the charge cannot disappear overnight. Okay? So what is going to happen is that whatever the charge stored previously in C1 is now going to flow all the way to C2. So that is exactly what happened. So now your V out is going to follow your C2 accordingly. Okay? So if you select the C1 and C2, you will find that V out and the input voltage actually follow the ratio of C1 and C2, which is not surprising because if you think about that, the charge stored in C1 is C1 multiplied by V in. The charge stored at C2 is C2 multiplied by V out, right? So you can see charge conservation, make sure that during these two phases, the charge should conserve. So in that sense, you will get V out C2 equals to V in C1. So therefore, you get the ratio V out actually equals to C1 V in divided by C2. Now if you select C1 equals to C2, then what you have is actually just a buffer amplifier. A buffer amplifier. So this is a unity gain sample and hold buffer amplifier. Okay? Now, here we assume the input voltage can achieve 1 volt peak to peak, and the op-amp with lead-lag conversion, so you can actually achieve pretty good bandwidth, and we neglect all other non-linearity effects such as op-amp offset and charge injection. Now, charge injection, when you do the switch on and off, the switch is not ideal. Okay, if you recall, NMOS transistor, when the switch is on, you actually have the electron hold underneath the gate. Now, when the switch is off, all these electrons underneath the gate has to disappear. Right? When it is on, you have electron underneath it. When the gate is off, the electron has to be disappeared. But where does the electron go? The electron go in both directions. They can go this way or they can go this way. But either way, all these electrons have to go up. So when they go out, they actually inject charge. So when you use the switch, potentially you could introduce injection charge error into the circuit. So here we are ignoring it. So we try to simplify the view. Of course, all this secondary effect is going to be reviewed if you really want to design a high-performance ADC. Here we just try to understand how the bandwidth and how the gain actually affect the ADC performance. So let's ignore this secondary effect first. So here you can analyze the switch capacitor. Actually, this is a switch capacitor circuit. You can see there is a switch, there is a capacitor. So this is a very well-known switch capacitor circuit. So during phi 1, you can see that the VC1 equals to Vin, VC2 equals to 0. During phi 2, your voltage VC1, okay, becomes VR over AV. It is not exactly 0. Why? Because you have VR over here. So this point, although we say virtual ground, but it's not exactly virtual ground. It's actually given by VR divided by the gain of the amplifier, AV, over here. So therefore, we have this thing over here. And then your C2 during phase 2 is going to be this voltage. So same thing, because here we have VR over AV, here we got VR. So therefore, you can take the voltage difference between these 2 points. So now, the total charge difference for capacitor 1 is basically the capacitance multiplied by the voltage difference between these 2 phases. So we use the superscript 2 and 1 to indicate which phase. So 2 means phase 2, 1 means phase 1. So you take the voltage difference. During phase 2 is simply this voltage. During phase 1 is Vin. So you can actually estimate the charge difference during the phase 2 and phase 1. You can do the same for the capacitor C2 as well. So during phase 2 is actually this guy. During phase 1 is usually 0. So now due to charge conservation, so whatever the charge difference in C1 should be equal to the charge difference in C2. So you equate them. And after some algebra manipulation, you can predict VR over Vin equals to this guy. And you see that VR over Vin is not exactly 1. It's not exactly 1. Okay, it's only approximately equals to 1. So there is an error there. Okay, the error is predicted by this guy over here. So now given the op-amp gain, let's say in this example we use op-amp that we designed earlier, you can have a gain of 63 dB, which is equivalent to 1,380. Okay, so the difference between the VR and the Vin is about 1.5 millivolt, which means your VR cannot follow Vin exactly. Your VR and Vin will be differ by this small amount, 1.5 millivolt. How do I know? Predict by this guy. Okay, you know that VR and Vin will be different by 1.5 millivolt. Now, this 1.5 millivolt will determine the error, because if there is no error, the difference should be 0. Your VR should follow Vin exactly. But now you see that V out doesn't follow V in exactly. V out and V in, they will be differed by 1.5 millivolt. This 1.5 millivolt, if it's less than the ADC LSB, you're okay, because it doesn't cause 1 bit error. But if it's more than 1 LSB, then it means that it will cause ADC error. So 1.5 millivolt is equivalent to how much LSB? We already covered that. The input is 1 volt peak to peak. So if I want to figure out the LSB, I just divide by 2 to the power n. So if it's 10 bit, it will be about 1 millivolt. For 10 bit, the LSB is going to be about 1 millivolt. Quite straightforward, because 10 bit is 1000. So 1 over 1000, about 1 millivolt. So obviously, 1.5 millivolt is bigger than 1 millivolt. So there is no way you are going to get 10 bit. So from this exercise, you know that the maximum bit that you can go is probably 9 bit. With this in mind, if I want to design 10 bit, what can I do? What can I do? Should be straightforward, right? What caused the error? The gain. So if I want to have more resolution, my OM gain has to be larger. Am I right? It has to be larger. So this gives a very straightforward illustration. Why people want to aim for higher gain? Because of this. The higher the gain, the smaller the error voltage, and the higher the ADC resolution. Okay? Now ADC, the resolution is one thing. Another thing is speed. How fast can you run the ADC? Now here, this error is so-called the finite gain error. So for finite gain error, you can solve it by using larger gain. But there are other like offset voltage and charge injection, okay, that will cause the resolution even lower. So don't miss thinking that, okay, I know this relationship already, so let's push the gain. Make the gain becomes 10,000. Then I can get down to 11 bit, 12 bit. No. By the time the gain error is no longer the limiting factor, other things come in. So you have to start thinking, okay, if offset voltage is bigger than 1.5 millivolt, I will still make the error. So what can I do? So you have to start thinking, can I do offset cancellation? Cancel with offset, right? And then if there is charge injection causing the issue, then your thinking is that, can I somehow eliminate charge injection? And all this is actually possible. Okay, offset cancellation we'll introduce later. Charge injection error, there is a so-called technique called bottom plate sampling. So with bottom plate sampling, you can somehow eliminate the charge injection error. Okay, so there is another simple way, just now using the charge injection scenario. The derivation is kind of complicated. You can see that I have to go through all these writing just to get what is the gain error. But you can actually analyze in a very simple manner. Loop gain. Loop gain can be designed or derived quite easily, because for loop gain, right, you just look at the circuit, break the loop, introduce this guy that is AV, and then you feed back, you actually have the so-called capacitor divider. So therefore you have AV multiplied by 1 over XC1 divided by 1 over XC1 plus 1 over XC2. So it becomes AV multiplied by C2, C1 plus C2. So you can actually derive the loop gain in a very easy manner. Now, what is the feedback gain? We know that from the closed loop, okay, closed loop function, we say the closed loop is equals to A, 1 plus A multiplied by F. If this thing is much, much bigger than 1, then this whole thing simplifies into 1 over F. That is the final gain, right? So we already know 1 over F, because we derived the thing saying that 1 over F is simply the ratio of the two capacitors. We derived that, right? because we say C1 V in equals to C2 V out. So V out over V in equals to C1 over C2. And that is basically closed loop. So it's 1 over F. So that is what we are getting. So it tells you you can actually obtain the feedback factor also. Now, if this is loop gain, which is given by F multiplied by A. F you already know. A you don't know. Can you figure out A? You can, right? So this is what I do. AF equals to this guy. A, I want to find out. F, I already know. So therefore, A becomes this guy. Now, why do I want to do this? Because once I know the A, once I know the F, I can actually rewrite this closed loop function in this manner. So then I can put down AV, C1, C1 plus C2, and then 1 plus AV, C1, C1 plus C2, multiplied by C1, F is C2 over C1, over here. And then you can actually simplify this thing and eventually get the following. So this is using the loop gain method to actually derive easily what is the gain error. What is the gain error? Now, how about for the speed? So we already determined in the previous lecture, we already determined these OM actually have the so-called GBW 23 megahertz. The phase margin is about 78 degrees. Actually, to be frank, you can further widen the bandwidth because 78 degrees is over them. You can actually make it slightly under them to get phase margin of probably 65 degrees or 60 degrees. By doing so, you can actually widen the bandwidth further to make it bigger than 23 megahertz. The good thing, now your OM can actually operate in a faster manner, higher bandwidth. So here we have to look at two settling behavior. One is due to the linear settling behavior, which is determined by the bandwidth. So this guy is simply given by 6.9 omega k. Okay, 6.9 omega k. Now, there are another nonlinear settling behavior, which is determined by the capacitor and the maximum current that you can do. So there are two things that limit the nonlinear behavior. One is the output load capacitance, CL. Another is actually the Mueller cap, CC. And both are limited by the maximum current that is 1 milliampere. So you can actually determine which one actually has smaller slew rate. So it turns out CL actually has smaller slew rate. The one that has smaller slew rate is going to be the bottleneck. Okay? So now you can see, you can use this smaller slew rate to determine the settling behavior. So let's assume your ADC will start from 0 and suddenly go all the way up to 1 volt. Okay? This is the worst case scenario. Usually it doesn't happen that way because sinusoidal like this, you don't jump from here right away to here. Okay? You jump from here, go to this step, and then further go to this step, and then further go to this step, and eventually you go to this guy. Okay? So from 0 all the way to the peak, that is the worst case scenario. So with the worst case scenario, you jump from 0 volt to 1 volt. If that is the case, your slew can be calculated using 1 volt divided by 100 volt per microsecond. So this shows that you will require about 10 nanosecond. 10 nanosecond. And then, once you reach the voltage that you want, you will start exhibit linear settling behavior. And this linear settling behavior, using 6.9 tau, is going to give you about 48 nanosecond. So altogether, the settling time is about 0.058 microsecond, so about 58 nanosecond. And you know that for this ADC, whenever I sample the voltage, it has to be settled within half the period. Half the period. So therefore, this settling behavior has to be smaller than half my sampling time. And using this, I can deduce my ADC at most can only operate at 8.6 megahertz. Not fantastic. Okay, 8.6 megahertz is considered slow. So now you can see the most limiting factor, sorry, I have to take a seat. The most limiting behavior is actually the linear settling behavior, because it takes about 48 nanoseconds. And that is determined by the bandwidth. So if you are able to widen the bandwidth, here in this case we are using lead lag. So you have to start thinking, can we use lead composition? If we use the lead composition, I can widen the bandwidth further. Okay, if I do that, and of course, do I really need 78-degree phase margin? Can I lower it down to 55 or 60 degree? Okay, if you're able to do that, then you can further widen the bandwidth, and that will significantly cut down the settling behavior. And when this guy no longer becomes dominant, then another thing comes into play, the slew settling. So for that one, it's very easy. Either lower the cap or increase the current. Okay? So that is how you determine the sampling behavior, the sampling time or sampling rate for the ADC. So with this simple example, we are showing you how the different OM parameter is linked to the application. Okay? Now, in reality, your linear settling behavior could be even smaller because of the parasitic. What do I mean? Now, if you look at the loop gain, the loop gain just now we are talking about is actually we only consider the capacitors C2 and C1. Okay? So this loop gain is actually given by this guy, which is larger. With a larger loop gain, your bandwidth is actually wider. Okay? But with the parasitic capacitor throw-in, so with this parasitic capacitor throw-in, now your loop gain is actually going to be smaller. And with this smaller loop gain, your bandwidth is going to be even narrower. So with parasitic, actually, it will actually affect your settling behavior to be even slower. Okay? Now, another thing is about the bottom plate sampling. So I keep mentioning this. So what is actually bottom plate sampling? We'll probably go through that later. So here's the simulation. So let's see. We all do all this calculation, hand calculation. Is it meaningful? So we run the sampling time, and then we try to see how long does it take to settle. And you can see that from 0 volt settle to about 1 volt. Okay, it shows that the settling time is about 0.048 microsecond. Okay, and the error is about 2% error. Okay, so if you really want to settle to 1% error, you probably need longer settling time. Now, what is bottom plate sampling? Now, I draw the capacitor purposely in this manner, so the curve one indicates bottom plate. Okay, bottom plate. So here, bottom plate sampling simply means that you turn off this switch earlier. You turn off this switch earlier. So think about this. You turn off this switch, you are actually injecting some error, some charge error. Because I already mentioned for the MOSFET, when you turn it off, the original charge store have to dissipate through this direction or this direction. Now, if we dissipate down, it go to ground, no issue. But if we dissipate up, it's going to affect the capacitor charge. Therefore, it is going to introduce additional sampling voltage error. Okay? So that one cannot be avoided. And then now you turn off phi 1. So let's call this guy phi 1E. E stands for early. I turn off phi 1 early, followed by phi 1. Now, when you turn off the phi 1, the charge will also go both directions. But the strange thing is this. If you look at the capacitor behavior is whatever the positive charge here, I will also have the same equivalent negative charge. Agree? It cannot be like one side got 3 electrons, the other side only got 2 holes. It doesn't happen that way. They have to balance out. So now, if let's say the charge want to go this way, let's say it's a positive charge. I want to go to the capacitor C1. the other side of the C1, is there any way it can draw the negative charge? It cannot, because this switch is already open. This switch hasn't closed. So where does the charge come from? It cannot. So in this way, you are actually forced. All the charge has to go back to the input. You get the point? Because the charge want to flow this way, but the other side say, don't come. If you come, I cannot entertain you. Right? So the charge have no choice but to go away. So that is the bottom plate sampling. Now, you're probably wondering, but still when you turn off this guy, it introduces error. So how would this guy help me? Now the good thing about this is that when you turn it off, the charge is always constant. Because the way it operates is either 0 volt or close to 0 volt. It's actually signal independent. It doesn't depending on the input. It's either 0 or close to 0. Okay? Now, if you introduce the error here, you are going to be in big trouble. Because depending on the input voltage, if it's 0.5 volt, you introduce different error. If it's 0.2 volt, you introduce different kind of error. So the error now is actually input dependent. You don't want the error to be input dependent. Because if the error is fixed, that is easy to eliminate. Am I right? If you know that the error is always like this, it doesn't matter. You know that, you can take it out. It's just an offset error. Better yet, if you apply differential circuit, okay, and you see that you always introduce error here, you always introduce error here, but they are always the same error. So differential circuit, if the error are the same, they cancel out. Right? So using this kind of bottom plate sampling and differential architecture, the charge injection error can actually be eliminated. That is the bottom plate sampling. Okay? Okay, so now we start looking at different kind of op-amp. So in the previous lecture, we talked about conversation, but we mainly focus on two-stage op-amp. Two-stage op-amp. So now we look at other kind of op-amp. The first kind that we are looking at is the so-called telescopic. So telescopic, you can actually get high gain with just single one stage. So this is actually one stage op-amp. Because if you look at it, the way they boost the gain is using cascode. Using cascode at the output. So by using the cascode to boost the output resistance, the PMOS and the NMOS, you make the resistance very, very large. And therefore, the gain becomes higher. Now, the circuit shown on the left-hand side is the high swing cascode method 3 that we introduced. Okay? You just make sure all these transistors are very large sizes. So this will give you approximately VTH. Okay? So this guy will give us VDS. And then you just add another VGS to get this thing. So if this is also VDS, then here becomes 2 VDS. And then you can just simply add the VGS. So this is a very simple high swing cascode method 3. You have gone through the homework 2, so now you know. You don't need very complicated calculation. You just make the sizing the same. Make sure one of them is large so that you get the VTH. And then the current ratio is basically the sizing ratio. Okay? From the simulation, you know that is not always true because square law is not being obeyed strictly because we are talking about sub-micron devices. So short channel length will have the effect there. Okay? But the way we design, once you got this guy preliminary result out already, you either tune the current and some of you actually tune the sizing. Either way is fine. Either way is fine. Okay? Now, in terms of the characteristic, this guy actually have high input resistance, high gain, and high output resistance. The problem is basically the limited input and output common mode range. And the compensation, the good thing, compensation, very easy. You just need the load capacitor, the lag compensation to compensate the whole circuit. And it can be very easy to stabilize. Okay? Now, what do I mean by limited common mode range? What is the minimum voltage this guy can go? You can see that the minimum voltage it can go is basically VDS set plus VGS. So V input common mode minimum is simply equals to VDS set plus VGS. What is the maximum it can go? Now the maximum it can go is limited by this guy. Because this guy will force down VB1 minus away VGS. Okay? It will force this voltage at most to VB1 minus away VGS. And then you can force this guy down further to VDS set. Finally, you add back the VGS. So if VGS equal, cancel, you see that the maximum voltage it can go is actually VB1 minus VDS set, which is not great because VB1 is not VDD, right? So if it's not VDD, it means the maximum it can go is kind of limited. So the telescopic actually have limited input common mode range. How about output common mode range? So output, the maximum it can go is basically you'll be thinking, oh, very good, 2 VDS set. And then we have VDD minus away this guy. But that is wrong because it depends on your left hand side. If your left hand side is like this, the maximum it can go is actually given by VDD minus away 2 VGS. Absolute value because you have VGS here, you have another VGS here, and then you add back another VGS, so plus VGS, and then you drop down by the VDS set, so you minus away VDS set. So the maximum you can go is actually VDD minus VGS minus VDS set. So that is no good. How to solve this problem? We can replace this circuit with high swing cascode. So in high swing cascode, you only set this voltage, VGS. But here, you bias it in such a way that it will not be 2 VGS. It will be VDS set plus VGS. So by doing that, then you will be able to get the maximum voltage becomes 2 VDS set. Okay, that is the maximum input common mode voltage. How about the minimum one? The minimum one is again limited by this guy, VB1. So if this is VB1, you drop down by VB1 minus away VGS. And then the minimum it can go, you have to add back. So plus VDS set. So again, you can see this VB1 is limiting. You want the VB1 to be higher so that you can boost out the input common mode. But if VB1 is higher, you are limiting the output minimum common mode. So they are contradicting. So the telescopic is simple, but it's very difficult to design. It's very difficult to design. So we have gone through this analysis over here just now. You can go through this analysis yourself, but I hope by looking at the transistor, it make it clearer. How come I can derive all these results? It's very simple. You just have to make sure all transistor is in saturation region. Then you just have to figure out what is the VGS, what is the VDS set. Now, input resistance, notice that we are biasing using this guy. So the input resistance is going to see RB1 plus RB2. So it depends on what are the resistor that you are using. You might be thinking, is it going to be very big? Now, to be frank, in circuit design, this guy can actually be implemented using so-called pseudo resistor. So in pseudo register, what they do, this is pseudo register. Is this transistor on? Is this transistor on? It's actually not on, right? Because if the transistor on, it should look something like this. Okay, the gate and the drain connected together. But this guy, the gate and the source connected together. So it's like you almost don't apply any gate to source voltage. So there will be very limited current flowing through. It's actually the leakage current. And because of this leakage current is in nanoampere, 1 over nanoampere, you actually get giga ohm. So you can actually get very big resistor. Okay, giga ohm resistor. So that is not difficult to obtain over here. Now, how about the output resistance? The output resistance, if you look at the circuit, remember the table that we have derived very earlier? So the resistance over here is R04 multiplied by 1 plus Gm R02. So the total resistance is basically Gm R0 squared. Of course, the top one also the same. So altogether, you have this guy parallel with another Gm R0 squared, but it's still in the same order. So probably half Gm R0 squared. Okay, so here I simply just say that the resistor is this guy. And then in terms of the gain, you have to multiply by additional Gm, which is the transconductance of this guy. So therefore, the total gain is Gm multiplied by Gm R0 squared. So the gain is actually Gm R0, the whole thing squared. So this is very suitable for high gain. Now for bandwidth, very straightforward. We just have to do output resistance multiplied by the load capacitor. So that becomes your bandwidth. The non-dominant pole, I just pick this guy as the non-dominant pole, which is usually very, very high. Because the parasitic capacitance is small, the resistance over here also small. Okay? So therefore, the non-dominant pole is actually happening at very high frequency. So fundamentally, this can be treated as a dominant pole or single pole system. Single pole system. So very easy to compensate. Sometimes you don't even need compensation. So for compensation, you just do the CL. So this is actually lag compensation. You don't change the non-dominant pole. You can see that the non-dominant pole stay the same. By changing the CL, you are moving the dominant pole to the left-hand side. Okay? This is telescopic. Sorry for sitting down. I would prefer standing, but my body cannot take it. Now, folded cascode. Folded cascode is actually the same as telescopic. If you look at it, it's very similar to telescopic. But it tries to solve one problem facing by telescopic, which is the limited input and output range. And for this guy, because it doesn't stack so many transistors, when you try to stack it up, the folded, it folds to the other side. That makes it easier to manipulate the range. Okay? So folded cascode, frankly speaking, is very similar to telescopic, except that it tries to solve the limited input-output range issue faced by telescopic. So you can see the characteristic is the same. You have high gain, you have high R in, you have high R out. Okay? You have larger input and output common mode range compared to telescopic. So that is the advantage. And then sun compensation, same thing as telescopic, also using CL. So in fact, although it looks slightly complicated, but it's actually effectively the same as the telescopic. So single pole system. You can go through, we'll go through this guy again, but you can see R in is again probably RB1 plus RB2. And then the output resistance, same thing. You see that is also proportional to GM R0 squared. And therefore the gain multiplied by GM, so it becomes GN R0 squared. So very similar to telescopic. Bandwidth also the same. Non-dominant pole the same. Okay? So in terms of non-dominant pole, you don't move it. You use the CL to change. So basically you only change the dominant pole for compensation. Now let's take a look. Input common mode range. So the minimum, same thing, VDS set plus VGS. This is the minimum it can go. How about VIC maximum? Now if you think carefully, I look at this circuit. The maximum I can go is actually VDD minus away VDS set. And then I minus away another VDS set. Okay, with the absolute, it means the PMOS. Without absolute, it means the NMOS. And then I plus the VGS. And to be frank, if you look at this guy, usually VGS is much bigger than VDS set. So therefore, very highly, this is going to be bigger than VDD. You get the point? So input common mode range, fantastic. You can go beyond VDD. So for this design, it's better than telescopic. How about output maximum and minimum? So output minimum. Okay, remember, I can actually make this guy becomes high swing. So the output minimum is simply given by 2 VDS set. Okay, of course here, because I cascade 2 diode connector transistor, it is going to be VGS, I think, plus VDS set. Okay, not great, not great. But I can change this guy into the following. Do this, and then you bias this guy, and you can actually make the minimum voltage go all the way down. Okay? How about Vout maximum? So Vout maximum now is determined by VB1. So with this VB1, you can add back this guy, so it plus the VGS, and then you subtract away the VDS set. Now the good thing is, now this VB1 only determines the output. It doesn't determine the input. So if you want the design to be as high as possible, you just need to make the VB1 larger. If you make the VB1 larger, then the whole thing can be very high without the bottleneck. The previous design telescopic, you see that the VB1, if you try to satisfy input common mode, you have to sacrifice output common mode. If you try to satisfy output common mode, you have to sacrifice input common mode. But for this guy, you only have to satisfy one. And you can make the output common mode also very high. That is photo cascode. Now, of course, all these cascode make the gain higher. We already know how to make the gain higher using 2-stage. Now, what if we combine the cascode with 2-stage? We can make the gain even larger. So this is telescopic already. With this telescopic, you add 2nd stage, also cascode. Now your gain is tremendous, right? So you will get very, very high gain. I probably would say very, very high gain. High input resistance, high output resistance. Okay, the input common mode range is limited, not surprisingly, because this is telescopic. But output common mode range is not. Okay, and you can use leak-lag compensation because now you have 2-stage. So with 2-stage, you can use leak-lag compensation to actually widen the bandwidth. Is limited input common mode range a problem? Is this guy a problem? This is a true-false question. So how many say yes, it's a problem? Nobody? How many say no, it's not a problem? How about the rest? You want to quit this module? Too many homework and project. I use this OM example. How will this voltage change? How will this voltage change? Will it change? According to OM negative feedback, what is the negative terminal of this voltage? It should be virtual ground, which means virtual short to ground. So this guy is approximately 0. Throughout the operation, it should stay at 0. Am I right? Hardly change. And that is why you find that limited input common mode range usually is not a problem. Because in the negative feedback operation, your OM input better don't change. Right? Because it is virtual short. The voltage is fixed, virtual ground. So it hardly change at all. So using this guy telescopic, we are actually making use of the characteristic of the OM. Input doesn't change. So even the input range is limited, no issue. Right? No issue for me. But output is not. Output, you want it to swing as high as possible. So you better want to have larger output common mode range. Okay? Now for this guy, interestingly, let's look at the gain. Now, you already know telescopic provide you GM R naught, the whole thing square. Right? Now, for two stage, this guy cascode also provide GM R naught square. Is that correct? GM? Oh, not really. GM R naught. GM? No, hold on. GM, correct. GM R naught square. GM R naught square. Okay? This cascode also provide you the gain GM R naught square. So, you have two stage. These two gain multiply together, you're actually getting GM R naught to the power 4. So let's say previously, telescopic and photo cascode, you already get 1,000. This guy is going to give you million. Okay? So this is a very simple design to boost the gain. And I hope you appreciate now, just now what do we say? In ADC design, you want to make the gain larger, so the error becomes smaller. So using this one, you can easily do it. Right? You can easily do it. So in terms of the bandwidth, this is two stage. So we can use the Mueller cap, multiply by the gain, and then multiply by the output resistance, not output resistance, output resistance of the first stage. And that actually gives you the dominant pole. We have analyzed the two-stage amplifier before, so you know Mueller cap multiplied by the gain of the second stage. So let me make it clear. So this is the capacitor multiplied by the gain of the second stage. So your capacitor gets boosted up, and then multiplied by the output resistance of the first stage. That becomes your dominant pole. How about your non-dominant pole? Your non-dominant pole, the way you do it is consider this guy short circuit. Okay, this is not there. You have 1 over GM 13 because it's a diode connected transistor. Can you see that? Okay, and then you will see by short circuit, this guy you see two cap. One is on the left hand side, and the other is on the right hand side. But CL, of course, is going to be big. So therefore, the non-dominant pole is going to be CL, and then with the resistance 1 over GM13. Okay? And with link-like conversion, we will try to make this guy the same as this guy, so that they will cancel out. Okay? They will cancel out. Now, unity gain bandwidth, okay, is governed by the GM2 CC. So this is what we derived earlier using the two-stage amplifier design. So it's very straightforward. Now, same thing for the VIC minimum, maximum. I believe you can go through yourself. I don't need to go through in detail. Okay, very straightforward. You just need to ask yourself, what is the condition such that all the transistor is in saturation region? That one you can figure out. Now, in terms of the compensation, it's actually using pole splitting. So by using the CC, you can move the second pole to the right-hand side. You can move the dominant pole to the left-hand side. So pole splitting. So ideally, it can actually allow you to achieve wider bandwidth, lead-lag compensation. Now, we have gone through OM design. Just now, the output is always single-ended. Single-ended. So what we covered is this guy. And you know this guy in a lot of commercial off-the-cell. So we call it COTS. COTS. Commercial off-the-shelf component. Okay? You can find many of this kind of OM. But in IC design, usually we design this way. We prefer this one. Differential input, differential output. So this thing have one key drawback, complexity. If you look at this guy, this thing has only one good thing, less complexity. But actually has a lot of bad things. In terms of the common mode noise rejection, I didn't say that it is not there. It is there. Okay, you can still achieve pretty good common mode noise rejection. But because the output is single-ended, so it's not that good. Okay? And then the dynamic range, because the output is only single-ended, let's say it can only go from 0 to VDD. So the dynamic range is also limited. Okay? Availability of signal with both sides, what do I mean? Now, if you consider the output here, output positive, it has to be positive. Okay? You cannot flip it. But for this guy, if you look carefully, it has quite good characteristic. Let's look through one by one. What do I mean by common mode noise rejection? Now, for this guy, if the noise is here, they cancel out. So it doesn't appear. But what if somehow the noise couple here directly? There's no way you can get rid of it. You get the point? Okay? But for this case, if you look carefully, now, noise here, no issue. They cancel out. But if, let's say, the noise directly appear here, because we are taking the differential output, we are taking VOP minus away VON. If the two noise appear at the output identically, when you subtract them, they cancel out. So that is the beauty of differential signal. And I hope you appreciate why in analog IC design, we always keep emphasizing we prefer differential signal. Okay? We like signal to go hand by hand, differentially. Because very commonly, you always have the signal corrupted by noise. And if they go hand in hand, if they corrupt in the same thing, when you look at the differential path, they cancel out. So differential signal is actually a very good way to eliminate the noise. So in analog IC design, we always prefer differential. Now, large dynamic range, let's consider. We already say this is from 0 to VDD. If you look at this guy is from 0 to VDD. But this guy is from VDD to 0. So if you look at VOP minus VON, the maximum you can go, you take VDD minus 0, so it will go to VDD. The minimum it can go, you take 0 minus VDD, it can go to negative VDD. So in terms of the output signal, it can go from negative VDD all the way to positive VDD, all because you have differential signal. So the dynamic range here is 0 to VDD. But with differential signal, you are going from negative VDD to VDD. So double. So there is another good thing for dynamic range. Now, availability of both signal, both sign, what do I mean? Now, if you want to get positive signal, you use VOP minus VON. What if you want to invert the signal? You just need to take VON minus VOP, right? You get my point? So, the signal is there. You want to get negative, very easy. You want to get positive, also very easy. They are all there. That is the beauty of having signal with both sides. Here, let's say this is V out. What if I want to get negative V out? What can I do? You have to introduce a gain that is negative 1 so that the output becomes negative V out. There is no other way. You have to introduce additional stage to invert the signal so that you will get negative V out. But with differential signal, you just have to decide which input to take first. You take the positive minus negative, you get positive. If you take the negative minus positive, you get the negative. So very easy. So in terms of the architecture, it's actually very similar. Whatever that you have previously, now you just get exactly the same counterpart, except that the output is differential. So the difference is that just now the single-ended cases, you notice that they are not symmetric. Let's take telescopic, for example. Just now you notice that this side is not exactly the same as this side. You are using diode connected transistor. But with differential, they are actually appear to be exactly identical. You see the left-hand side and the right-hand side, they are identical. They are identical. And you can bias this guy and bias this guy in the same manner using high-swing cascode. Using high-swing cascode. And the output, you no longer take from one output. You actually have to take from this side and this side. So it will be always differential output over here. Okay, so this is differential telescopic. The analysis is exactly the same as previous one. So nothing tricky. Now the only difference is that with differential, what is the DC at this point? You don't know. So therefore, it required additional circuit called common mode feedback. That is what makes it complex. The common mode feedback makes the differential circuit complex. Okay? Now, why you need common mode feedback? So let's consider this. You can look at this guy and consider it as a current source. NMOS current source, it looks like this, right? Agree? You can look at basically just a lot of transistor stacking. So high swing, or not say cascode current source, not say high swing, cascode current source. So the current look like this. And because it's NMOS, so it look like this, V out. If you look from the top, it's another current source. Am I right? You have two transistors stacking, so now you have another current source. But because it's PMOS, so it go like this. What is the final output voltage? V out. Intercept point, right? Agree? So you might be thinking, great, this is the intercept point. But when you design the PMOS and the NMOS current, can you guarantee that they will always meet at the middle? Let's say PMOS current is smaller. So PMOS current is smaller, so you move down. You intercept here, right? Now let's say if it's even smaller, you intercept here. Agree? What if the PMOS current is larger? Let's say here. So it could happen anywhere, am I right? Because you cannot determine what is the PMOS current. You might be thinking, don't worry, I simulate. So I make sure they will intercept at this point. By now, you guys has already run corner simulation. Can you guarantee that your PMOS is always typical? You cannot, right? Let's say you design based on typical, you achieve here. You are unlucky. After fabrication, the device coming back, your NMOS is actually at the typical corner, but your PMOS is at the slow corner. So your current is going to be smaller, right? Your PMOS current. So you end up having intercept here. Let's say you are lucky. Your PMOS turned out to be fast corner. Then you end up here. But no matter what, there is no guarantee that you will be here. Get the point? Because in the fabrication process can go anywhere. It can go up, it can go down. That's why we have 5 corner. Typical, fast, fast, slow, slow, fast, slow, slow, fast. And your design, you only look at one. You have to run all the corner to make sure that it works. But you see that for this case, it's very difficult to make sure that it will always happen at the middle. So what you want to do is that let's automatically adjust. What if I find that my PMOS is slower? So which means my output voltage now is actually at the lower voltage. So after operating, I find that, oh, my Vout is actually at the smaller voltage. Doesn't matter, you feed it back. You feed it back through here, so you compare it with what you want, which usually is half VDD. And you find that right now, because of the process, my Vout average is lower than my VCM. What will happen? If Vout is lower than my VCM, all the current flow here. Agree? If the current flow here, this voltage is going to rise. Agree? Okay? If this voltage is rising, so this voltage is rising, which means this current got larger. Okay? If the current got larger, Pi higher, higher, so the current got larger. So this thing is actually getting lower. Let me see. Did I analyze it wrongly? Output CM smaller than VCM. ID9 actually gets smaller, not larger. So where did I go wrong? So this guy go down. All the current flowing through here. Oh, sorry. If the current flowing through here, this voltage actually go down, not go up. Right? Now, if this voltage go down, this current actually reduce. So ID9 actually reduce. Here. Now, if ID9 reduce, so what it means is your ID9 reduce. So just now I draw the circuit, right? Your PMOS is actually here. Your NMOS is actually here. So your intercept at this point. Now, because your ID9 reduced, so now your NMOS is actually reduced, right? ID9 reduced. You are actually moving this intercept point to this point. Get the point? Okay? So using this kind of common mode feedback, it determines if my PMOS is slower, I know my output voltage is lower. So through this negative feedback action, I will try to lower the NMOS accordingly so that I will bring this point back to the supply voltage, back to the middle point. You might be saying, how do I know where to back? I need to move it. Would it overshoot? Yes, it will. But don't forget, if it, let's say, overshoot, go up too much, you compare with this guy, what will happen? Then this thing will go smaller, and this thing will go up. And this NMOS current will go back again. So you just keep adjusting the negative action until finally it settles nicely such that your Vout common mode is approximately equals to what you want, VC. That is the beauty of common mode feedback. Differential folded cascode is the same as telescopic, except that it have all the advantage that we mentioned before. Larger input common mode range, larger output common mode range, okay? But exactly the same characteristic as folded cascode previously. But now you can see both paths are actually symmetric. And when you look at output, you have to take the differential output. You take this side and this side to form differential output here. And similarly, because of the differential output, you have two current sources. There is no guarantee that you always get the middle point. So you use a common mode feedback circuit, try to measure the average of the Vout, compare it with the common mode voltage. So now you see that if the Vout is lower than VCM, let's say this case, it will cause ID9, this guy, to go down. Okay? Because if this guy is lower, all the current flow through here, so this voltage will actually go down. If the voltage go down, this voltage go down, this current will also reduce. Because this current reduce, so this voltage will actually go up. Okay? So the other case is the opposite. You can go through the analysis yourself. Differential two-stage. Same thing as the two-stage cascode that we covered before. But now you can see everything is symmetric. Left-hand side and right-hand side, they are symmetric. Even the lead-lag compensation, you cannot just do one side. You have to do both sides accordingly. I didn't show the common mode feedback, but the principle is the same. So you go through the analysis, you will see that if the output common mode go down, okay, let's say this guy is smaller than the common mode voltage. So if it go down, smaller than the common mode voltage, what you want is that for this voltage to go down also. Because if this voltage go down, you will try to increase this voltage back up. Okay? If you don't understand this thing, you can try to draw. NMOS current look like this. PMOS current look like this. So if it's going down, it means initially it's like this. Okay? Initially it's like this. Now, if this guy is going down, you have to increase the PMOS so that it becomes something here. So your red dot can move to the right-hand side. So your goal is trying to increase the PMOS current. And that could only happen by lowering down the V common mode feedback. So you can use this kind of current source concept to figure out how should you adjust the common mode voltage. So let me repeat again. Just now I didn't draw very nice. So let's see. This is your NMOS current. And then your PMOS current look like this. So let's say intercept here. Now the only thing that you need to adjust is actually the PMOS current. So to adjust the PMOS current, you want to intercept here. Because NMOS you didn't change anything. So it doesn't change. So the blue line stay the same. The only thing that you are adjusting is actually the top, which means the red curve. And you know that if I want to intercept at the center point, I need to move the red curve up. So you need to move the red curve up. So to move the red curve up, you will notice I need to lower down the VCMFB. Because lowering down the VCMFB will increase the PMOS current and cause this intercept to move back to the center point. So you can easily figure out the common mode feedback action by considering it as a current source, NMOS and PMOS current source, and then you can figure out which direction you should move. There is other case of common mode feedback. So what is the issue with this kind of common mode feedback that we talk about? What is the issue with this? Anyone? No issue? the circuit I show you is perfect. This is connected to Vout, which means connected at this point. Agree? What is the output resistance at these 2 points? Gm R0 squared. Agree? Which is very high, right? Right? Now, if you don't pick R to be very, very big, so your output resistance is going to be this guy parallel with R0P plus R0N. Initially, you want the output resistance to be big, but it could be limited by this guy, because this is real resistor. Of course, you can use pseudo resistor, but the problem with pseudo resistor is that if you pick the resistor too big, it settles very slowly. It settles very slowly. So the problem with this resistor is that usually you use real resistor, but you have limited size. But you want this output resistance to be big. So if you use the real resistor, it could end up very, very big. If you use the pseudo resistor, on the other hand, the area can be small, but it is too big, bigger than what you want. In that case, you end up very, very slow settling. Take an example. The output resistance could be, for example, 1 mega ohm. So in order to make this guy doesn't affect the final output resistance, you probably want to pick this guy to be 10 mega ohm. Right? If you use the pseudo resistor, you could end up having giga to tens of giga ohm. That is more than what you want. Fantastic, but you don't want it. Right? Because too big, it means settling time is super slow. But how do you implement 10 mega ohm? Use the real resistor. So you have to lay out very long, right? Because resistor is proportional to the resistivity, proportional to the length, and inversely proportional to the area. So to get very big resistor, you have to have very long length. So it will take out area, a lot of them. Okay? So what is the better way? So that's why we bring you to this common mode feedback. Your output P and output N are not connecting to resistor. Instead, it connected to the gate. Connected to the gate is infinite resistance. Am I right? So it doesn't load the output resistance. That is the good thing. Okay, it doesn't load the output resistance. Now, how does this work? So if you look carefully for this guy, actually is using the reciprocal bias concept. So you see, I mentioned this before, reciprocal biasing is actually a very powerful concept. The whole concept is you create two exactly similar branch. If this guy behaves like that, you expect this guy to behave similarly because they are twins. That is the purpose of reciprocal bias. So here the branch that we want them to function is this guy. You set up this guy such that this is the common mode voltage that we want. Let's say equals to half VDD. You set up this thing such that if this is half VDD, this voltage will be set up properly, and then I can bias everything properly. Now this guy also behaves the same. You don't use this guy to directly control your current source. In fact, you use this guy to control your current source. So if your output voltage move up, you can see the common mode voltage also move up, right? So you have higher current in that case. If your output voltage go down, you also have the common mode voltage go down. But how do I know that it finally settled? It settled if these two voltage average equals to VCM. When that is happening, your common mode voltage is also same as this guy. Okay, that is how it adjusts the common mode voltage without the loading effect. So this is a popular circuit to achieve common mode feedback. Another way is the so-called dynamic common mode feedback. This is very popular in switch capacitor circuit. So in switch capacitor circuit, you always switch in the capacitor. So in the common mode feedback, you actually don't need op-amp. You can use the capacitor to transfer the charge so that eventually you achieve the common mode feedback voltage that you want. The good thing, it doesn't draw any current. Everything is about switching. So let's analyze the circuit. So during phi 1, you can see that during phi 1, your C1 capture the voltage VCM minus V bias. Okay. Here also capture VCM minus V bias. So you have two C1, left side and the right side. Your phi 2 is open. So actually you also capture the C2 voltage, which is given by this guy. If you're wondering how do I get the second term, very simple. You have V out P minus VCMFB multiplied by C2, and then you plus VCMFB minus V out N multiplied by C2. If you simplify this guy, the other way. I make a mistake. So here, you can say V out P minus away V CMFB multiplied by C2. This, you will get V out N minus V CMFB multiplied by C1. You add them together, you are going to get this term. Okay? Straightforward. Then during phi 2, switch is open, so this guy closed. Now the C1, C2 combine, so you actually have combined cap on both sides, C1 plus C2. And the total voltage is simply given by the same thing. You take this voltage, subtract this one, and you take this voltage, subtract this one. Therefore, you end up having the following. Now take note that the CMFB at these two phases, phase 1, we call it CMFB1. Phase 2, we call it CMFB2. Okay? These are two different phases. So in charge conservation, we will make C1 equals to C2. So by doing that, you just have to do some simple algebra manipulation. You end up having the following expression. Now you know that for this expression at the steady state, what will happen? At the steady state, the CMFB for phi 1 and phi 2 is going to converge. So CMFB2 equals to V CMFB1. So this term disappears to 0 at steady state. And then at steady state, you want this voltage to settle to VCM. So this guy will settle to, this guy will settle to V bias. I'm wrong. Yeah, sorry. So this one we already make sure this guy go to 0. And then we look at this one, we will see that at steady state, your output average voltage will be equals to the desired common mode voltage that you set. So this guy cancel. So eventually your common mode feedback voltage will settle down to V bias. Now the only thing that you need to pay attention to is the design, C2 and C1. So for this guy, you need to make sure C2 is about 10 times of C1. So the key idea is that this voltage capacitor is big, so every time you only change slowly. Now this guy is small, so that every time you try to transfer a little charge from CM and V bias back to this guy. Okay? So at steady state, when you keep changing or charging, transfer the charge, you only change the final voltage, this guy, a little bit. So if you think about this thing using the water analogy, this is like a big bucket. A big bucket. This is like a small bucket. So during the operation, every time you try to pour the water in. So initially you don't know what water to pour. But let's say you pour the water enough, to fill the water bucket to half the tank. You know that you already reached there. Okay? So once you reach there, so then every time you actually don't pour much water because it's already settled. So the whole concept of having C1 much smaller than C2 is like every time you pour a little bit, so you only change a little bit. But at steady state, it doesn't disturb. Okay? That is the whole analogy by choosing capacitor to be much bigger. Okay, I'll make a break here, but before we go, I forgot to ask you guys a question last time. So let's see whether you still recall. Can you scan this? Poll everywhere. Done? You guys have done homework 3. So should be piece of cake. All done, right? So let's see. Lecture 5. Let's play. Should be piece of cake, right? Basically, which one will achieve higher bandwidth? All done? Do I have to wait until 0? Wow. Surprisingly, I thought this one should be a piece of cake. How come? How come? The leg one should be the smaller, right? So the leg one should be the smaller. That leaves you either this guy or this guy. Okay? So for these two, please pay attention. Final exam is coming. So those guys or girls who pick these two, pay attention. You guys don't understand conversation. Now these two, okay. Lead leg and lead, I can understand the confusion. But remember, lead leg means I cancel away the 0. Lead means I make the 0 so much that I even cancel away the pole. You get the point? Okay? So one is going even extreme so that I can cancel away the pole. So therefore, the lead is actually achieving much higher bandwidth. Okay? So 40%. Okay, let's see. Only 1%? This guy is fast. Do we just throw dice? Or you see that 100 megahertz, so you just pick 100 megahertz. Surprisingly, only 8 students attempt. The rest don't bother to calculate. Wow. I thought you guys just did the homework 3. So for this one, I mentioned, in frequency consideration or M, there are two bottlenecks. Either the bandwidth or the slew rate. So if you consider the unity gain bandwidth, because we use the unity gain buffer, so of course the maximum frequency is 100 megahertz, right? But if you consider the slew rate, what you want to do is 2 pi f multiplied by the voltage has to be smaller than the slew rate. 2 pi f multiplied by the output voltage, 1 volt, has to be smaller than the slew rate. So using this equation, the bottleneck is actually the second one, the slew rate. So because of that, if you go in calculation, you see that, calculate, and you are going to see that actually using the slew rate, the frequency that it can sustain is only 31.8 megahertz. So you compare the two. Using the bandwidth, I can go all the way to 100 meg. But using slew rate, I can only go all the way up to 31.8. So you pick the slower of the two. Okay? So slew rate is going to be the limiting factor. Yes?
So the answer is 100 divided
100, no. Yes, correct, 100 volt per microsecond. Not this 100. 100 volt per microsecond divided by 2 pi. You're right. 2 pi 1 volt actually. So a lot of students just divide by 2 pi, forget about the output voltage. It's just that in this case 1 volt, whether you divide or not, it doesn't matter. But I could set voltage to be 0.5 volt. I could set the voltage to be 2 volt. Then it will matter. Get the point? So I calculate wrongly? Is that right? Could be 100 divided by 2 divided by, 100 divided by 1 micro divided by 2 divided by pi. Oh yeah, you are right. So there is no solution? Yes, correct. The solution is D. You are right. The solution is the D. Why do I consider this guy? I know why. Sorry. I said the question, I don't even understand myself. Now, if the supply is actually 1 volt, think about that. What is the peak voltage that you can go? No? So a lot of time you talk about all amp. You guys are consider this thing, right? 1 volt, 0. Agree? So your sinusoidal should fluctuate between 0 volt and 1 volt. Agree? It cannot go to negative, right? Because the supply is only 0 volt and 1 volt. I didn't say supply positive, negative, right? So what is your sinusoidal peak? 0.5 volt, right? Agree? So therefore, 2 pi f, what is the maximum peak voltage? 0.5. Has to be smaller than the slew rate. Volt per microsecond. So therefore, your f is actually less than 35.8 megahertz. I'm right. I'm not left, I'm right. Okay, let's take a break here. Maybe we can resume around 8 o'clock. Is that fine? Okay, let's resume at 8 o'clock. I hope there's not going to be a delay lecture tonight. Let's see. High performance op amp. So just now we introduced how to actually achieve high gain like 2-stage with cascode, right? But besides very high gain, there are actually other things that we're interested in. For example, we talk about offset, how the offset voltage rise about. For example, mismatch in the IS, mismatch in the register, so on and so forth. So how do we achieve low offset op-amp? And how about low noise? We want very low noise op-amp. So how can we do that? High gain, we already talked about that. Another is actually high output driving capabilities. So let's take a look. So low offset, there are a few techniques that we can do. Common centroid, that is mainly about the layout. We'll talk about that. Using resistor load and trim it. Now that is expensive and irreversible process and not very good because over time the performance actually deteriorates. Chopper amplifier, that is what circuit people prefer. We use circuit technique to actually get rid of the offset. There are problems associated with it also. And then offset sampling is another kind of circuit technique. So let's take a look. So common centroid, here I didn't draw the transistor, but if you think carefully, offset voltage, the most important thing is actually the input differential pair. Okay, input differential pair. It's a transistor. Now this input differential pair, if it is big, for example, you don't want to just lay out them like two side-by-side transistors. If it's big, you will try to lay them out in a common centroid manner. So what do I mean by common centroid manner? So for example, you can chop the transistor, each transistor into two. So one transistor you could split on the top left and another on the bottom right. The other transistor you use top right followed by the bottom left. Okay? Now how does that help? So if you think in the process fabrication, they always have some systematic bias. Systematic bias meaning that, for example, when I do the implantation, it might not be vertically, it might be slanted at a certain angle. If it's slanted at a certain angle, for example, so it could be here, this guy, this side, actually experience more implantation. The other guy that is further away experience less implantation. Now that is from the left-right perspective. How about top-bottom? Let's say the implantation, let's say I do this, okay? It could also be in this manner. So if you look carefully in terms of process variation, there could exist process bias in the sense that either the left-hand side is slightly different from the right-hand side, or the top side is slightly different from the bottom side. Now if that is the case, if you look at how we lay out the transistor, if we lay out in this manner, we try to cover all the possible difference by combining the gray one, top left and bottom right. You are trying to compensate the effect because I have transistor on the left, which has left side bias. I also have transistor at the bottom right, which also compensate my right side bias. So if you look in this manner, if I have left right and top bottom bias, so this guy will have left and top. This guy will have right and bottom. Now similarly, this guy will have right and top, and this guy will have left and bottom. And if you look at this guy, both transistors will cover L, R, B, T. Get the point? You see, the gray one, it will cover LT, also RB. The yellow one will cover L, T, and RB. So in this manner, they sort of compensate all the process gradient. And it make the transistor matching better. Okay, matching better. Now here, take note of this guy. It doesn't work for random variation. What does it mean? Now this is great in terms of process gradient, meaning that you know left side always different from the right side, top side always different from the bottom side. But random, when you talk about random, how would the top vary with the bottom? Let's say there is no process gradient. So top could be larger, bottom could be smaller. Top could be smaller, larger, bottom could be larger. You don't know. Because that is what random is all about. It could go either way. So common centroid doesn't work if there is no process gradient. So when you read the document about the PDK, they always talk about mismatch, Pilgrim coefficient, mismatch. These are actually random variation. So if you use common centroid, it's not going to help you getting rid of this. You get the point? This exists no matter what. You try to use the process centroid, common centroid, to try to overcome thinking that you will make it better, it won't. Because random is like noise. It's always there. You cannot get rid of it. Okay? Register trimming. So this is very expensive. Why? Because it requires manpower to test the device. So you test the device seeing that, oh, this guy, the offset voltage is 10 millivolt. Then what do? They can use laser. So supposedly, in the differential pair, they actually have register. So what they can do is they can then use the laser, try to trim the register. If you want the register to be smaller, then you try to trim to make the width to be smaller. Trim away. So in that case, you can make the resistance to be larger. Because when you make the width smaller, register becomes larger. So in that case, you can actually trim while monitoring. So you keep measuring the input voltage or output voltage, and then you trim it, see whether you can get the result. So this is actually very expensive because you need to continuously monitor what is going on. So you need manpower to do it. And then you also need to trim it. So usually if you look at those very low offset or sometimes they sell very high price. Why? Because they actually use the manpower, try to make them high performance, low offset according to what you want. Therefore, they can afford to sell you higher price. The engineer cost is involved. Okay? And another way is like you don't need to use the laser. You can build in some fuse, or we call it anti-fuse. So what it does is you blow the fuse, because when we talk about fuse, when you blow it, it becomes open circuit. But in this case, it's called anti-fuse because when you blow it, it actually becomes short circuit. So supposedly you have a bunch of them, and you decide you want the resistor to be smaller. So you blow it so that you no longer get the R. Okay? So now it becomes R plus 2 delta R plus 4 delta R. So the resistor becomes smaller. This is anti-fuse. The problem is that unlike the trimming, it's not continuous. You cannot continuously change the resistance. The resistor is quantized. You can only change from R, delta R, to delta R, so on and so forth. Okay? But the good thing is that you don't need laser. You just have to, how do you blow the anti-fuse? You just need to pass a big current. You pass a big current going through this guy, so this diode conduct. When it conduct, it actually burn, and then therefore it forms a short circuit through the diode, and it becomes shorted, provides shorted connection across the resistor. Both process are very expensive, as I mentioned. You need to monitor and then adjust. Another issue is irreversible. Once you make the resistor smaller, you cannot make it becomes larger. Okay? Or you make it larger, you cannot make it become smaller. You cannot reverse the process. What is the issue with this? People get old. People get old. You cannot reverse and becomes younger. Same thing, this guy, you might be thinking, I already get the offset to be very, very small, so it should stay small. But in reality, it doesn't. Because in reality, when you keep operating it, when the current flow through, the device gets heat up. When you get heat up, the implantation probably have different kind of distribution. Okay, all the resistor becomes different aging process. So the resistor could also becomes different again. So initially it might work great, but after certain time, it go back to provide you poorer offset again. Okay, so this is very expensive and it cannot reverse. Also, it doesn't continuously work. after a certain time, it go back to become worse again. Okay? So circuit technique is actually better in that sense. Because circuit technique, they know what is going on. They try to think of a circuit that actually try to get rid of this effect. So chopper amplifier is one such circuit technique. So let's consider what happened. So this is actually the op-amp, and you actually have offset present over there. So before you start using this op-amp, before you do using the op-amp, you try to chop it. You chop the signal. You chop the signal by providing the switch such that the input either connected to this terminal or connected to opposite terminal. So you can see during phi 1, this signal just passed through, so you have this kind of connection. Output also passed through. But during phi 2, the connection actually gets swapped. Okay, so you actually got this kind of connection. So it depends on phi 1 and phi 2, your input and output get swapped. Now, how does that bias? Now, if you look at this chopping, it's actually like mixing. What it does is like the input coming in, it can become positive or negative. Because the way you connect to the input is like I swap. If you are swapping, the concept is actually similar to multiply by positive and negative, alternatively. That is chopping is doing. So in frequency domain, this is your input, which is here, input. By doing chopping, you are actually multiplying it with a positive negative square wave. So you are multiplying it with certain frequency, FC. By multiplying it with FC, your input actually gets shifted to FC. So when you observe the spectrum at this point, you see that your input is no longer occurring at DC. It's actually occurring at certain carrier frequency, FC. And then when you add it to offset voltage, your offset voltage happens here, which is far away from your out converting signal. Okay? Now, once you have this guy, you sum them, and then you go through the amplifier, this whole thing actually gets amplified. So here, basically, if you look at this output, this thing becomes larger, this thing also becomes larger, because they get amplified. Okay? Now then, at the output, you chop it back. You chop it back, it's like you multiply it again with the same frequency. So if you multiply by the same FC frequency, you get two components. One is that you move this guy back to DC. Another is you move this guy up to 2 times FC. Right? Cosine omega t multiplied by cosine omega t, you get two things. One is at DC, so half. Another is actually 2 times the frequency. You get these two components. So one is at DC, another is twice the frequency. But for the offset voltage, which is originally at the DC, then you basically just get out converted to higher frequency, FC. Now then, at the output, it's very simple. You just filter. If you filter it, if the offset frequency is far away, okay, you don't need very sophisticated filter. You can suppress this offset to a very low level. So that is chopping technique. It's using frequency domain thinking. I try to translate the offset voltage to higher frequency, and then I can use the filter to filter it away. That is the concept. This concept also applicable to flicker noise, because if you think about flicker noise is actually low frequency noise. Low frequency noise. So when you use this technique, it doesn't matter if it is DC or low frequency noise, because they center around here. So therefore, the noise can also get eliminated using this chopping technique. So it sounds wonderful. Am I right? What is the problem? Come again? What is the problem with the switch? The switch has the resistance, but if your amplifier have much higher resistance, it doesn't matter, right? Nowadays, the technology is so advanced, I can always reduce the resistance of the switch, right? And if the frequency that you're operating at is not that high, then it's not a problem. Come again? Charge injection using differential one, you can actually do it. Like I say, if they introduce the same thing for both paths, it doesn't matter. They cancel out. What's the issue? One of the issue, if you think carefully, here, if I don't have anything, I only need to amplify up to this bandwidth. Am I right? Yes or no? After chopping, I need to amplify up to this bandwidth. Agree? You didn't see it. Supposedly this is up to plus minus 100K. My chopping frequency cannot anyhow select. I need to select it high enough. So most likely I will select it to be probably 500K. So this becomes 500K plus minus, so 600K, 400K. What is the M bandwidth that I need to amplify? Plus minus 600K. Get the point? So nothing is free. It sounds wonderful. I remove the offset. I remove the flicker noise. But think of it. By introducing chopping, what you are doing is basically converting a low frequency signal to high frequency signal. That's what you're doing. So your circuit also need to deal with high frequency signal. Which means in your design, your bandwidth need to be wider. So you are trading off bandwidth with performance. You are making it wide band so that you can remove something that you don't want. But you know, to make the whole thing wider bandwidth, you need what? To make the circuit operate faster, you need what? You need money. What is the direct trade-off? Higher frequency. Higher frequency require what? Higher frequency require what? The unity gain bandwidth is GM over CC. So, to get higher bandwidth, you need lower cap. Lower cap required better technology. So that means more expensive. Another way, you need higher GM. Higher GM means higher current. It means higher power. Okay? So this is the trade-off. Now, another way is actually to use the offset sampling. Okay? So, assuming no offset, we already covered this previously. So, no offset, the input charge is CSV in, and then the output charge is CSV out. CV out. So, therefore, output and input voltage can be formulated or derived based on the capacitor ratio. Okay, that is under no offset consideration. But if there is an offset, now you have to use superposition. Superposition means that, let's consider no offset. You have this guy, so you got this value. So far, so good, right? Now, then during the second condition, consider this guy ground. Now you only consider this voltage. You see that with the offset voltage, it's actually forming a non-inverting amplifier. Non-inverting amplifier, where this guy is appearing here, and then this guy actually go through. So if you look carefully, this looks something like these cases. CS, C. Non-inverting, right? It doesn't look like non-inverting. The reason it doesn't look like non-inverting is because Originally, the voltage source is appear here, right? Yes? But the voltage source appear here, it means this guy is ground. If now I move it to here, are they the same? They are the same, right? There's no difference, right? I put the voltage here, positive, negative. It's the same as I put the voltage here, positive, negative. Both are the same, right? Because what is the voltage at this point? VOS. What is the voltage at this point? Also VOS. No difference. Okay? So if you look at this guy, you know that this is actually a non-inverting amplifier. Because the gain is basically 1 plus CS over C. Okay? So here, the issue is you have gain for your input. You also have gain for your offset voltage. So your offset voltage actually get amplified. So how to solve this problem? We can make use of the switching clock phase to sort of memorize what is the offset voltage during one clock cycle. And then during the next clock cycle, remove it. So here, during phi 2, you close this switch, you close this switch, and you close this switch. Okay? So by doing so, the circuit reduced to the following. And what is happening is that you see that this offset voltage is being stored across the CS and also the C. So during phi 2, your voltage at the capacitor CS is equals to negative VOS. So take note, the curly side, okay, the curly side of the capacitor. And then your capacitor C is actually VOS. Then during phi 1, this guy is closed, this guy is closed. So you are ending up having the following circuit. So with this circuit, now during phi 1, your voltage across the CS is given by V in minus away this offset voltage. Your voltage across the capacitor C is VOS minus away VL. Now, charge conservation guarantee that the changes in the charge across the capacitor CS is basically the voltage difference at two different phases. So if you do that, luckily, one is VOS, another is VOS, so they cancel out. And you end up having the charge without the offset voltage. Same thing during the finding the difference of the charge across the capacitor C, you take the voltage difference at phi 1, the voltage difference at phi 2, and you see that the offset voltage also get cancelled out. So the whole principle about offset sampling is that you make use of two clock phase. So make sure that you capture the offset voltage during these two clock phase. When you try to measure the charge difference, this offset voltage cancel out each other. So they are not there. That is the whole principle. And by doing that, you can end up having the output voltage totally independent of the offset voltage. That is called offset sampling. And this offset sampling is also useful in terms of noise. You might be thinking, what I'm sampling is actually a DC voltage. How come it's good for flicker noise? Think of it this way. Flicker noise is low frequency. So for low frequency, it means the noise voltage that you sample changes very slowly. So if I capture the noise at this instant, most of it is going to repeat in another instant. So if you cancel it, although they will not be fully cancelled, but most of it will be cancelled. Okay, that is the characteristic of low frequency noise. Low noise amplifier So for low noise amplifier, we make use of this concept. If you split the amplifier into multi-stage, okay, the noise of the later stage becomes less of an issue because that noise will be overwhelmed compared to the amplified signal. So for example, the noise for the second stage is here. The noise for the first stage is here. Out of these two stages, this noise is less of a concern. Why? Because compared to this noise is going to compare with the signal amplified by the gain, A1. So this is signal. So this noise is less of a concern because it's much smaller compared to the amplified signal. Your signal already amplified. But if you try to look at this point, your noise at this point is going to be comparable to your signal because your signal didn't get amplified. So the whole concept for low noise is trying to split the amplifier into multi-stage and then try to focus on the first stage. Introduce some gain on the first stage. By doing that, you try to make the subsequent stage noise negligible or less significant. But of course, that only solves one problem. You try to make the noise of the subsequent stage less significant. But how about the noise for the first stage? You can try to make it smaller by using larger device. You can also make it become smaller by using different kind of device. For example, PMOS usually exhibit smaller noise compared to NMOS. Okay? So if you want to get low noise design, a very common technique, try to use PMOS, don't use NMOS. Okay? And then why larger device can have smaller noise? Now, that come to this concept called flicker noise. Now, flicker noise, what people observe is that flicker noise is due to the imperfect manufacturing. So if you look at the MOSFET, okay, this interface is not perfect. This imperfect interface between the oxide and the silicon will trap electron. But when they trap the electron, it doesn't mean they always trap it. Once in a while, let's say the electron gains sufficient energy, they will break free. So what you see is that the electrons sometimes get trapped, sometimes get released. These are noise, right? It's like initially you expect current to be constant, but once in a while, electron get released. So there's a spike in the current. Or the electron get trapped. So there's a dip in the current. There is noise, right? So this imperfect state contribute to the noise, and that briefly explains why PMOS is better, because somehow when you fabricate the PMOS, they have less of this situation. Okay, so the flicker noise becomes smaller. Now, another thing that helps is like if you have larger area. If you have larger area, think about this. Noise is an averaging behavior, right? Noise is an averaging behavior. So somehow, if you think, if I have more trap, it turns out to be more noisy. But if you look at noise, noise is actually sum in power. But signal is sum in amplitude. So if you try to think of it, your signal will increase by, let's say there are two of them, signal will increase by 4 times in signal power, right? But noise will only increase by 2 times. So overall, how much do you gain? You gain square root 2. So although it looks like the more the noisier it is, but if you think in terms of the device, when I have larger device, my current add in amplitude, but my noise only add in power. So overall, if you consider it, you actually gain in terms of the noise behavior. So using larger device also help reducing the noise. And another thing, circuit technique we mentioned before, you can use chopper, you can use offset sampling, both help to reduce the flicker noise. Now, gain boosting amplifier, this is actually this is actually trying to, trying to make the output resistance even larger, and therefore the gain becomes even higher. Okay, so the principle is very simple. We already know R out. Due to this feedback action, the R out is going to boost out by the loop gain, and the loop gain in this case is simply A, because if you go through the loop gain is A. So therefore, the R out is boosted by the loop gain, 1 plus A. A simple way to boost the loop gain is using this single stage transistor, and you will see that the gain gate feedback is simply GMR. So GMR. So therefore, the output resistance gets boosted up by this guy, which is very small. And one issue is that the minimum output voltage is now governed by VGS M3 plus VDS. Not good, because if without this one, the minimum it can go is actually 2 VDS set. Okay? But what if we use OM to do that? So if we use OM to do that, then we can actually set this guy to be VDS set, which is controlled by this guy. Because this is an OM, so using the virtual short, I can actually make VA equals to VREF equals to VDS set. That is the beauty of OM, right? Virtual short. And how much gain is being boosted? If you look at this guy, you break the loop. You see that the loop gain, because this is cascode, so you actually get boosted gain by GM-R0. And this R out is boosted by this gain. So overall, your output resistance is boosted by GM-R0 squared. Okay? So the beauty about using OM to boost the output resistance is that you are able to set VA arbitrarily. So you can make it becomes VDS set. So it doesn't sacrifice the voltage swing. Not only that, by using cascode, you can actually make the gain not GMR, but GMR squared. So you can boost the gain further. Now, there are issues with this gain boosting OM. If you look carefully, this is the OM. If you look carefully, I'm just replacing this guy with a simple OM symbol over here. Now for this OM, actually there is a pole over here, because at this pole, you see the gate capacitance of the transistor, and this guy actually have quite large output resistance. If you look carefully, you can see here, you have a cascode output resistance, so that is quite large. So there is actually a dominant pole for this OM over here. And if you look at the loop gain actually I can rewrite it using this single pole system. So the dominant pole is simply determined by RC. So of course R is proportional to GMR squared, R0 squared. Okay? And the C is proportional to CGS. Now, in terms of the output resistance, we know that it is going to boost up by this amplifier gain. But not only the DC portion, you will also be boosted up by this frequency response of the OM pole. And if you rearrange, you see that the output resistance got the following. Okay? Try to manipulate. So eventually you take out 1 plus A, you get the following. These are just simple algebra. So you can see that the output resistance get boosted up by this factor, 1 plus A. But you also introduce one pole and one zero. The pole introduced, we already know, is exactly the same as this guy. But the zero, if you look carefully, the zero is actually improved by the loop gain. Okay? A improved by the loop gain times of the pole. So if you try to plot out the output resistance frequency response, so at the DC, low frequency, you get this guy, which is what we want. We want the output resistance to boost up by the factor 1 plus A. Then, due to the dominant pole, due to this guy, you see that the impedance start to drop. But once you reach this guy, due to the zero, it flat out again. And then now the output resistance reduced to R02. So it doesn't boost the impedance all the way. At high frequency, it reduced to exactly the same resistance as only one transistor, R02. Now this output impedance is going to be parallel combined with the capacitor at the output, which is here. We are going to connect it to CL. Remember, this is op-amp, right? So for op-amp, we will always put the CL at the output. So it's going to be parallel with this CL. How does CL looks like? The CL looks like the red curve, because CL is 1 over SCL. So as the frequency increases, it just keeps dropping, which is exactly the red curve over here. Parallel combine these two, so the blue one is the ZL, the red one is the CL. Parallel combine the two, the smaller one dominate, right? When you parallel combine ZL with 1 over SCL, the smaller one dominate. That is the characteristic of parallel combination. So if you look carefully, when you look at the red and the blue, initially the blue one dominate because the blue one is smaller, right? And then after beyond this point, the red one start to dominate. So therefore, I should follow the red one. But I didn't draw exactly the red one. I tried to draw the black one that is slightly smaller than the red one. Slightly smaller. And then beyond this point, I see the blue one flatten out. If the blue one flatten out, now I can be sure everything should be follow the red one. Right? Because now when you have two things approximate, one parallel with 1 million, you don't care about 1 million, everything should be 1. Right? But during this portion, I cannot say everything equals to the red one. Why? Because during this portion, I'm considering 1 parallel with 100. 1 parallel with 100, you probably didn't get 1. You probably get 0.9 or 0.99, right? But 1 parallel with 1 million, you can say is 1. So therefore, you can see there are some small difference here. But beyond this frequency, everything is the red one. Now, after going through this thing, what I want to highlight is actually this guy. This looks like the doublet, isn't it? We covered last week doublet. You can see that it is dropping, flatten out, and then dropping again. But the difference is so small, you can hardly see it. You can hardly see it. So the problem with this gain boosting op-amp is you cannot get rid of this doublet. It's always there. So you have to be careful. If you are not careful, the settling behavior actually will suffer. So this is the paper that listed. You can see that using this guy, you can set the output voltage to be arbitrary to what we want, and then the gain can be boosted very, very high, 90 dB. Okay? It doesn't show the frequency response, but you can be assured the doublet is always there. Now, to be frank, I have been misused the term. I always tell you we are designing the op-amp. But to be frank, we are not designing the op-amp. We are designing OTA so far. What is the difference? When you talk about op-amp, you actually have very low output resistance. I can drive any load I want. That is op-amp, operational amplifier. So if you look at all the commercial off-the-cell op-amp, they always have a buffer stage. A buffer stage. It can provide very low output resistance, and you can connect to any resistance that you want. You can connect 100 ohm, no issue. You can connect 10 ohm, some op-amp can, some op-amp cannot. Okay? But 100 ohm, most of the op-amp don't have issue. They can drive it. But what we are designing so far, what we show you, actually don't have any output stage. In fact, we try to boost the gain by using very large output resistance. And this large output resistance will disappear if we connect to a small resistance. So you use the op-amp to drive 1 kilo ohm, you'll be doomed. You design the op-amp to have 90 dB, you connect it to 1 kilo ohm, suddenly the gain dropped to 10 dB. That is the issue with the op-amp that we are designing, because this kind of op-amp is called operational transconductance amplifier. Operational transconductor amplifier. It's not op-amp because it doesn't have output stage. This operational transconductor amplifier is very good in driving capacitor, because capacitor has infinite impedance at zero frequency. Okay, so the resistance is actually very, very high, and you can drive it. As long as the frequency of concern is not very high, you can always treat it like open circuit. So OTA is very good at driving capacitor, and that matches very well in what we want to do. For example, switch cap. You are designing capacitor, you are driving capacitor. Okay, so, or if you are designing, for example, GMC cell in the filter, you are driving capacitor. So OTA is very good if you are interfacing with capacitor component. But if you try to use OTA and try to drive resistance, for example, non-inverting amplifier in this case, I'm not saying impossible, but let's see what is the effect. What is the effect? So you can rederive this whole thing, assuming you have finite output resistance. So now your Vout, okay, what you need to do is your Vout is actually your Vin, subtract away this guy. Now this point is basically given by a resistor divider, and then you amplify it by the voltage gain AV. But after that, you are only obtaining this point. So to get to Vout, you actually have to consider this whole branch of resistor and go through a resistor divider. So after some rearrangement, you see that your output and input is governing by this guy. We go through this analysis before, but if Rout is negligible, okay, you can cancel them. We actually come out with the typical analysis of op-amp. But if Rout is not negligible, effectively what you have is that the op-amp gain is changes. Your op-amp gain is no longer AV. Your op-amp gain becomes this guy. Now you start to see the effect. So if you use R1, R2 to be much smaller compared to your Rout, your gain suffer, right? So for this kind of design, you prefer your Rout to be much smaller than R1 or R2. So think about that. If you are talking about using OTA with output resistance that is mega ohm, then your R1, R2 better use 10 mega ohm, right? But usually that is not possible. To be frank, it's not possible. But what we can do is, although we cannot make it much larger, we can make them comparable. So if Rout is comparable to R1 to R2, the loop gain will drop, but still you can get quite decent gain. And if you are not happy, just redesign so that the gain becomes larger. You can boost the GM, for example, make the gain larger. So although the overall gain dropped due to the finite output resistance, but because your GM is larger, so you sort of compensate. So you can do that. But if it turns out your R1, R2 is actually much smaller, let's say your Rout is mega ohm, but you design this non-inverting amplifier using kilo ohm, you are doomed. Because your gain now reduced by 1,000 times. You don't have much gain anymore. So to overcome this problem, you need buffer. So to complete another consideration is the effect of loading. So assuming R1 equals to R2, let's say I want to design input equals to 1 volt peak to peak. Your output equals to 2 volt peak to peak. Now if your R1 is kilo ohm, your op-amp only need to supply 1 milliampere, because 1 milliampere multiplied by the resistor kilo ohm, you are actually able to get 2 volt peak to peak that you want. But now if your R1 reduced to 100 ohm, now your current need to supply up to 10 milliampere in order to get 2 volt peak to peak. So beside the loading effect, this guy also causes issue in the current requirement of the op-amp. In order to achieve the voltage desired, you actually have to pump more current in order to support the low resistance used in this non-inverting amplifier. So to solve this issue, you can introduce buffer. One very common buffer is the so-called source follower. Source follower, what is the output resistance? We covered this one. If you look into that, so the output resistance is simply given by 1 over Gm minus Gm2. This one doesn't provide much gain. It only provides 0.8 unity gain, okay? But it provides very low output resistance. So now if you insert this one, you can actually drive kilo ohm, okay, kilo ohm resistance. This is what we call class A amplifier. It's not very efficient. The reason we call it class A is because the M1 is always conducting. It provides a constant current. So if M2 is conducting, okay, you need to conduct twice the current. So let's say M1 always consume I. M1 consume I. So if you want higher current, you let M2 consume 2I, and when this guy drives the output resistance, so I will flow to the output. Now if you want I to go back to the input, you just make sure this guy is 0. So no matter what, half the current is actually being wasted in M1. So this is what we call class A amplifier. So efficiency usually is very poor, about 50%. Okay. Not suitable for low supply. The reason is because if you look at the output maximum is always limited by this guy, subtract away the VGS. So you will never reach VDD. Class AB, so just now we addressed, because the bottom one always consumes constant current, so that is not efficient. So if we do this way, okay, what we can do is, when the voltage is high, we try to push this voltage to very high, this guy also very high, so in return, the current becomes 0. Because for PMOS at the bottom, if the voltage is high, the PMOS doesn't turn on. But this NMOS will flow to the output. Now you can see that the output current all go to the output. The top NMOS current all go to the output. It doesn't waste it at the bottom PMOS. Now when the voltage is low, when the voltage go low, so this guy go down, this guy go down. Now you have the other scenario. This guy turn off. Okay? Now all the current go through the M1 because now M1 fully turn on. So in this case, you have the cases where the current either only the top one working or the bottom one working. So this is so-called class AB, much more efficient compared to class A. Okay? The issue with this one is that linearity, because it's very difficult to guarantee that the switch over from M2 to M1 operation is very smooth. So usually if you observe the output, you could observe something like this, crossover distortion. That kind of thing. So this will cause the distortion, class AB. Now in terms of the output resistance, depends on whether NMOS or PMOS is working. If it's PMOS working, no body effect, this guy. If it's NMOS is working, got effect, you got this guy, but usually the impedance is very small. And then the gain, if it's PMOS, you got unity, NMOS, you get about 0.8. Okay? Output, again, they are limited because maximum is limited by input subtract away VGS, assuming this guy can go to VDD. Minimum, assume this guy can go to 0, then this guy is actually another VGS. So either you get this guy or this guy. So the output swing is actually limited. To solve the output swing problem, so people sometimes don't care. They just use common source. You can also make this resistance very small. For example, if this device is very big, it draws a lot of current, you see that the output resistance is given by 1 over lambda ID. And because ID is so big, the output resistance It will not be as small as just now the source follower, but it can reach probably kilo ohm. So using that, you can actually still drive the output that is kilo ohm level. So the output resistance R02, but bear in mind, this is 1 over lambda ID. So with buffer, ID usually is big. So this guy could be in kilo ohm or hundreds of ohm level. It's still possible. And the gain is GMRL, okay? Because RL usually is very, very small. So GM, even the GM is big. So the GMRL actually, it can provide gain, but it's not very large gain like 100,000, that kind of thing. Probably 1, probably 2, that kind of thing. Okay? In terms of the output maximum and output minimum, now because you are using common source structure, you actually only have to care about the VDS set. So it can actually go very high swing. This is another class AB, okay, push-pull. So you can see this is push-pull. So when the input go high, so this current flow in this manner. Due to the current mirror, the current flow in this manner. Okay? Since no current flowing through, this guy is cut off. Okay? Now, when the input go low, so no current flow through here, but current now go through in this manner. Due to current mirror, it go through in this manner, no current flow through. So it's exactly the same point. This is actually combining just now the class AB, but is using the common source architecture instead of the source follower. Another concept, RM nonlinearity. Now here we are using conservative estimation. We talk about this guy. We know the gain is given by 1 plus R1 over R2. So this is the RM gain. But this RM gain will actually introduce error, and the error is actually can be reduced or deduced using the loop gain over here. And closed loop, this is the desired feedback. This is actually the one that contributes to the error term. Now if you try to plot the result, this is what we have been deriving, which is 1 plus R1 over R2. Okay? This is given by the blue one. We always predict that. But if you consider this one, which is the error term, you actually end up having the red curve. The difference between the two, that is the error. That is the error. We use this to estimate the resolution of the ADC. But in terms of nonlinearity, now nonlinearity, when you try to plot the curve from the starting point to the end point, nonlinearity means that the curve that you are getting is not linear. There will be curve. But this curve, no matter how they curve, they cannot exceed this region. So if you look carefully, actually this curve, the maximum difference is actually governed by this delta Y2. So what you get is actually the black curve, which exhibits some nonlinearity. Okay? What you expect to get is the blue one, which is 1 over F. What you can get in the worst case is the red one. Okay? So you can deduce the black one, which is somewhere in between. If you want to estimate the distortion is actually related to delta Y2, because that determines the curvature. Nonlinearity is all about the curvature. The more curving, the more nonlinear it is. So delta Y2 actually predict the distortion that you can get. But to estimate delta Y2 is very difficult, am I right? Unless you know exactly how the black line looks like, you cannot estimate delta Y2. But you can actually estimate delta Y1 quite easily. And what you come to deduce is that I can predict my distortion is always less than delta Y1. You get the point? So this is setting the boundary of the distortion. So although you cannot get exact estimation, but you can you can estimate the theoretical worst case. The theoretical worst case is the linearity cannot be better than this guy. The actual linearity is governing by this guy. Okay? So then how can we predict? So for example, let's say you have unity gain buffer, peak-to-peak signal, 1 volt. And based on just now the estimation, we can predict delta Y1 already. And the error is given by this guy. We figure out the loop gain. So we can predict the distortion is actually less than minus 63 dB. But in fact, we will expect the distortion to be much smaller because this is actually the theoretical maximum bound, the upper bound. Theoretical upper bound. Okay? So let's do the estimation. So in LTSpice, you can actually run the total harmonic distortion. In Cadence, what you can do is that you run the transient. After running the transient, you can run FFT. Okay? And then you try to see what is the harmonic. You will see third harmonic, fifth harmonic, all the harmonic. You can sum all the harmonic together. Okay? And then from here, this actually tells you the total harmonic distortion. So basically, it's sum third, fifth, seventh, all the harmonics sum together. And this number, if you want to predict how many dB, you just have to take 20 log THD. Okay? So 0.0126%. So you divide by 100. And then you take log. And then you take 20. If you do that, you'll find that the distortion is actually 78 dB. If you look at our prediction, 63. So actually what we predict is the worst case. Okay, very conservative estimate. The good thing is that you don't have to run the simulation to get the result. You can sort of estimate quickly what is the expected distortion. Okay, so we try to run this simulation and we find that the distortion is actually this guy. Okay, it's actually less than 57 dB. But here we predict it to be minus 78. What is the difference? The difference is that if we don't use the unity gain buffer, let's say in this case, sorry, where am I? In this case, I simply, without any loading, I just do this. I don't put any register. So therefore, the gain is exactly what I predicted, 63 dB. Then the distortion is actually quite high. But now, if I put the loading, my op-amp gain actually dropped. If you go and analyze the gain now actually dropped by 17 dB. It's only 48 dB. So if you actually estimate the distortion actually should be estimated to be less than minus 48. But the actual simulation tells you minus 57. So it tells you, by looking at the gain, you can actually predict the distortion quite accurately. Okay? Not accurately, quite conservatively. It's always less than that. Now, that basically concludes everything that I want to cover about circuit. So here, I'm moving on to something more complicated, slightly more complicated, but probably more useful if you are actually dealing with the actual IC design. Now, nowadays, in IC design, we don't design pure analog circuit. What is analog circuit? Let's say you design amplifier. That is analog circuit, pure. What is digital circuit? Logic. Right? So in project 2, Prof. Ma give you the project. That project consists of digital circuit, the decoder. It also consists of the analog circuit. Right? So it's actually a mixed signal. It consists of digital and analog. So nowadays, a lot of time the circuit consists of digital, analog, and RF. What is the difference between these two? Now, before we understand this, we have to understand how the IC actually looks like. So this is the IC that you design. In the IC, you design a lot of pad over here. Now, this pad cannot be just floating. You have to connect it to the external world. How do you connect it to the external world? You need bonding wire. You need to bond it so that you bond it to the package, let's say DIP, and then when you plug the DIP to the breadboard, you can make the circuit work. Or you plug the DIP into the PCB, you can make the circuit work. But bonding wire is inductance. Any wire is inductance. So this guy is actually your die, the IC that you design. But after packaging, you have to consider they are actually inductor before it actually connected to the external battery source or the external ground. They actually have to connect to this wire. This is where students make the mistake. When they simulate or design, they always assume perfect case. This is my circuit amplifier. I connect to VDD right away. I connect to ground right away. So in the simulation, this is the circuit. This guy connect to supply. And this guy connect to ground. That is what you do. Am I right? Most of you do it this way. You didn't consider the wire. But in reality, this is what happened. There is a wire. And for wire, they always come with inductance. Let's see what happened. If you are talking about op-amp design, okay, you always have constant current source. The current is always constant, even though you have signal, because the current either go this way or go this way. But the total sum of the current is always constant. That is the beauty of analog. Because if the current is constant, even there is a wire, if the current is constant, what is dIdt? Zero. The current don't have gradient. But what is the voltage drop across the inductance? That is predicted by LdIdt. So there is always zero. If you put inductance at the ground, also the same. So for analog circuit, because the current is always constant, it doesn't matter. Even with the inductance, with the wire, it doesn't matter. It doesn't cause any difference. So it's like you are simulating this case. No issue. Because there is no voltage drop across the wire. Get the point? Let's talk about RF. So RF, a lot of time you only have single transistor. Right? But RF not that worse. Why? Because you talk about RF, the signal is microvolt. The current changes milliampere. And they change in sinusoidal manner. So not only they change very small, but they change in sinusoidal manner. So if you try to predict the LdIdt, so they have the sign, okay, yes, the frequency is large, the inductance is large, but the current is small. The current is small. So it does introduce some disturbance to the voltage supply, but it's not a lot. Okay, so in RF, you do have to model the wire effect, and they do affect the circuit performance, but not that much. Worse than the analog, but manageable. Look at this guy, inverter design, digital circuit. Now, digital circuit for inverter, either on or off, right? The current, most of the time is zero. But when you try to turn it on, suddenly you see the peak current because you want to charge out the cap. Or when you try to turn it off, you discharge the cap. So if you look at the wire, you see current spike. If you see current spike, you're actually seeing a delta direct function. When you do the LdIdt, this is the worst case. So if you have listening to discussion among the IC designer, they always say digital circuit noisy, digital circuit noisy. Now, digital circuit noisy, why it is still so simple to design? Because you only deal with two levels. 0, VDD. Your circuit is noisy, let's say 100, 200 millivolt. But as long as you have good enough margin, 0 to 1 volt, you have 1 volt margin. Even my supply is noisy, 100 millivolt. My ground is noisy, 100 millivolt. How many margin do I have? 800 millivolt. You get my point? So digital is noisy, but I don't care because I got margin. Right? So digital circuit is always noisy. Analog circuit always quiet. R circuit somewhere in between. Now, if you are designing separate circuit, that's very easy. Your life is very easy. But nowadays, a lot of time we want to mix. So your IC not only have analog, you also have digital. So when you try to plan your IC design, in terms of I/O, how should you arrange it? So here, I show you, you shouldn't have analog circuit and digital circuit in the same site. You shouldn't have it at the same site. If you want, you should have analog circuit and the digital circuit I/O to be orthogonal. Reason? How many of you still remember Maxwell? How many of you hate Maxwell? To be frank, I'm not a fan of Maxwell equation. I don't like microwave. But there are some rule that is very useful. Right hand thumb rule, something like that. A current flow through a wire. If let's say the current is in this direction, you can actually figure out the magnetic field, which is circular to this wire. You know that, right? That is A-level physics, right? So if you think, if the current for the digital is going in this manner, you are going to have magnetic field rotated in anti-clockwise if you are facing in this direction, right? Now this magnetic field is not limited to this region. It could actually be wider, right? Agree? Of course, the further it is, the weaker the magnetic field, but it's there. So this magnetic field, if you think carefully, electric current and magnetic field, they are vice versa. Current can generate magnetic field can generate current. Am I right? So if this current in digital I/O generate the magnetic field, this magnetic field coupled to the analog wire, they can generate back digital current. Am I right? So if you arrange the digital and analog I/O in a parallel, in the same side, so if this is the digital current, it generates the magnetic field. This is the coupled magnetic field. It can actually generate back the digital current. Am I right? What does it mean? The digital noise get coupled to the analog circuit. So it's not a good idea to arrange digital and the analog on the same side. If you arrange it orthogonal, you don't have issue, right? Because the current flow in this manner, the magnetic field go in this plane. There is no chance that it can couple to the analog. You get the point? So that's why you arrange this is better. Or you try to arrange this, also okay. Either opposite or orthogonal. Now let's say you are limited with the pad. You have no choice. But you have to arrange them on the same side. You are running out because digital got many pins. What can you do? What can you do? You can try to put this guy as VDD or put this guy as ground. Why? Any magnetic field, once it reaches ground, you will try to terminate there. You get the point? You learn about Faraday cage, right? Have you learned about Faraday cage? No? Have you heard of the term called Faraday cage? Yes or no? No? It's a very famous example. Outside, a lot of lightning, right? There is a cage. The person stay inside the cage, always safe, right? Because all this magnetic field eventually will get terminated by the cage. So it's the same concept. If you have ground in between even VDD is considered as ground, right? AC ground. So you have a ground in between the digital and analog. The digital few try to cross over, but they will terminate at the ground. And then it doesn't cross over to the analog. It doesn't affect that. Okay? So these are some of the things that you have to pay attention to. Now here is another dilemma that people always face. In my IC, I got digital and analog. But eventually there's only one ground. Right? So how should I separate the digital ground and analog ground? So there are 4 different possible ways. You know, for NMOS, there is always substrate connection. So the thinking is, where should I connect the substrate? Remember, for NMOS, the substrate is universal. It doesn't matter whether it's digital circuit or analog circuit. They are on the same substrate. So eventually you have to make a decision. Should the substrate connect to digital pin or analog pin? So one possibility, you can arrange in this way. First way, where all the substrate and the ground connected to analog ground pin. And the digital one, you try to separate it into the digital ground, because you know it's going to be very noisy. The second way, opposite, analog ground quiet, you keep it quiet. But the digital ground and all the substrate connected to digital ground. Second method. Third method, doesn't matter. Let's chop them equally. So transistor, if it's analog, I put analog. If transistor is digital, I put it digital. All the ground shorted. And then fourth cases. I know ground is sensitive. Let's put them for the substrate, separate one. Okay, separate one. So analog ground and digital ground. To be frank, I've gone through 3 cases. Out of these 4 cases, I've designed using these 3 cases before. Only one case I never use. So which case I never use? 1, 2, 3, 4. Come again? 1, 2, 3, 4. Which cases I never use? This is the last slide. 3. How many say 1? Nobody. Okay, good. How many say 2? Nobody also. 1. How many say 3? How many say 4? This case I never use. Think carefully. I want circuit to be quiet. Digital is noisy. If this guy is noisy, it means this point is noisy. Agree? If this is noisy, this is noisy. What is the current for this guy? You notice that the body can actually control the current. Am I right? If this is noisy, I can also inject noisy current here. So these cases, never use. Now, when I first started out, I was told to do this design. Okay? Substrate should be quiet, so we should actually tie everything together. Okay? Tie to the analog part. Make sure it is quiet. Digital one, yes, this is quiet, this is noisy. You will make the current noisy, but who cares? The digital got margin, right? So I don't care. So when I first start out, I use this. And then when I join company actually tell me I should probably use this if I have pin, right? So why not separate this one? Because sometimes this could be analog, this could be RF. It could also be noisy, right? So although not as noisy as digital, but substrate, I want it to be totally quiet. So there are people doing this design also. So later, I use this design. Now, here is when I start working with a research institute over here. I see that actually they do this. And the circuit turns out still okay. Even the substrate are separated. To be frank, I never understand this fully, because if you look at the substrate, right, there is a digital here, there is analog here, but the substrate, they are all connected together. The substrate are connected together. Come again? What ground cannot be separated? Yes. Yes, they share the same substrate. But the thing is that, if you think carefully, the substrate is not perfect resistance. The resistance is not 0. There will still be resistance over here. Okay, and the current prefer to flow in the least resistant path. So if you try to put, let's say P plus here, so if there's a digital noisy current, they will tend to be flow in this rather than flow all the way here and then get collected over here. So in some sense, it still works. Okay, and if you want to make it work better, you can put a deep end well. Because putting a deep end well, you are trying to make the resistance even larger. So you can isolate the digital part and the analog part. Okay, so to be frank, out of these 4 configurations, I've used 3. Okay, only this one, don't use it. Because it's very obvious. If the digital is noisy, substrate is noisy, it will affect the analog circuit, also noisy. So second cases, never use. Okay, so before I end the lecture, let's do this thing again. All done? Yes? Okay, let's go to activity. Lecture 6 and play. Okay, let's see whether you guys are paying attention. All done? Sounds like everything is Did I make it wrong? I think so. I thought photocascode is actually correct, right? I must not be thinking straight. Oh, this. I think I know why. I know why I put 32. I put the second one. Photocascode, what is the issue with photocascode? Same performance. So when you look at the same performance, I'm not just talking about gain. I'm not just talking about voltage headroom. I'm not talking about frequency. There is another important performance factor. What is that? What is that? Power. Right? Power is also one of the performance consideration. Low power, that is one of the performance factors that people always look at. If you look at the photocascode, one of the issue is the power is double. The power is double. Okay. Let's look at the second one. This one should be quite straightforward, right? No? I thought it should be quite straightforward. Can release the answer now? Okay, let's see. Correct. Okay, just now I already mentioned, PMOS actually has superior noise performance. So first stage is critical, definitely, but we should use PMOS instead of NMOS. So with that, I think I end the lecture. So good luck for the homework assignment. Today, 11:59, no penalty. What penalty is going to be imposed? I need to see how many people have late submission and how late. Okay. Project next Monday due. For mine, next Monday due. I don't know about project 2. Okay. If you got question, you can always email me.